Hey, good morning, everyone. Here we are in lesson 5. We're going to start working on basic derivative rules for functions. The first few are pretty simple. For example, in the constant rule, if you have a horizontal line, the slope of that line is 0. So in each case here, these 4 examples, using proper derivative notation, y prime of any constant function is just going to be 0 for that function. So that's pretty straightforward, easy to apply. Any constant function is going to have a 0 slope. The slope of the tangent line would also be 0 all along for any value of x in that function. Looking at the single variable rule, it's pretty much the same way. If I have any function that's y equals 1x or y equals 1t or x of t equals 1t, the derivative for each one of these functions would be 1. The slope of the line is 1, and the slope of the tangent line would have the same characteristics. It would be 1. So the equation is y equals 1x. The derivative graph, we could just sketch right here, f prime of x. The derivative graph is 1. F prime is 1 on my derivative graph. This is my position graph. This is my first derivative graph. Now, the great rule is the power rule. So when we have a power rule for any function x to the nth power, you can see the rule says that if I want the derivative of any x to the n power, I'm going to multiply the power n times the variable and then reduce the power on the variable by 1. So in this case, y prime is going to be 2 times the x, and then 2 minus 1 would give me power 1. In example B, f prime of x would be 4 times 1, or 4 times the x, and then reduce this power by 1, so 4x cubed. In the next two, we want to rewrite the function square root of x or rewrite the function g of x as a power. So I'm re-expressing the function. Instead of radical square root of x or square root of x, I'm writing that as a power function. Y is x to the half power. Then it's easy to apply that power rule. 1/2 times x and reduce this power by 1 means I have a negative exponent. So it's customary to not write a negative exponent. We would want to put the 2 and the x to the negative half back down into the denominator to write that as a positive power. And in this case, same thing. G prime of x is negative 1 times x, and reduce this power by 1, so negative 2 power. Then rewriting g prime of x is going to be negative 1 over x squared. So the power rule. A couple more on this one. F of x is 1 over x squared, or x to the negative 2 power. So f prime of x is negative 2x to the negative 3, which can be rewritten so that the power is positive. Negative 2 divided by x cubed. And then lastly, this is x to the negative 2/3 power. Our derivative is negative 2/3 x, and we're taking 1 off of that, so that's going to be negative 5/3. And then finally rewriting so that our exponent has a positive power, so we can call that x to the 5/3 power for our derivative graph. So those are pretty easy. And then to make that just a little more complicated and user-friendly, if I have a coefficient a in front of a power function, we're just going to do the same thing, only multiply our power times the a factor, and then again reduce the power or subtract 1 from the exponent in the function. So we'll give a few of those a try. In this case, y prime is 3 times 2, x to the first. S prime of t is negative 5 times positive 3, t to the second. In this one, again, we want to rewrite that as 6x to the 1/2 power. So the derivative would be 6 times 1/2, which is 3, and then x to the negative 1/2 power. And we said we could rewrite that to be 3 divided by x to the positive 1/2 power on the denominator. This one, same thing. I'm looking at 3x to the negative 2 power. So g prime of x is going to be 3 times negative 2, and x to the negative 3rd power could come downstairs and be negative 6 divided by x cubed. Here's 2 more for you to try. In this case, we have 4x to the negative 1/2 for my function f of x. F prime of x is negative 2 divided by x to the 3/2 power, because we're reducing this power by 1. And finally, negative 8x to the 4/3 power, which is negative, then y prime is negative 8 times negative 4 divided by 3. That looks like 32/3 positive. And then take 1 off of this power, which would be negative 7/3. So he comes downstairs, x to the positive 7/3 power. So y prime is 32 divided by 3x to the 7/3 power. Next, we're going to just kind of expand our knowledge. If you have a string of functions, you can take each derivative for each part of the functions. Let's say we had a polynomial, or if you had a difference, you can do the same thing, and just one piece at a time use the power rule or the general power rule. So let's give those a try. We got about 4 of those. F prime of x, this would be 3 times 1, x to the second. This is a subtraction, so we have a negative 10 x to the first, and 1 times 2 is positive 2, and if you have 1 and you take 1 off, that's x to the 0, and we all know x to the 0 is 1, and then this is a 0, so we're done with that one. Letter B, I'm going to give that one a try. We've got y prime is 5 times 2 divided by 5. So 2x to the 4th plus 4x to the 3rd plus 6x, and then the derivative of a constant is 0. Let's see, rethinking this, it looks like x to the 1/3 power plus 5x to the 1/2 power. This is my g graph, and I want g prime of x. This is going to be 1/3, and x reduced by a power of 1 is negative 2/3, so that comes down here. And then this one is 5 times 1/2, and take 1 off of that power is x to the negative 1/2, or the square root of x. Since I already wrote this one as a rational exponent, I'll keep this one as a rational exponent. And then lastly, we have several things going on. Remember, this is 4x to the negative 1, this little term right there. So y prime is 5 times 3 divided by 2. And then take 1 off of 3/2 is a 1/2. 6 times 5 divided by 3. And again, take 1 off of 5/3, so that's going to leave us with 2/3. And finally, 4 times negative 1 divided by x to the negative 2, which comes down here to be x to the positive 2. So derivatives of sum and difference. Oh, two more. So h prime of x is 6x, and think about this as 4x to the negative 2, so that's going to turn this to positive 8x cubed on the bottom. And then think about this last term as 2x to the half, so that's going to become positive 1 over square root of x. We're taking 1 off of that power. That negative half power goes in the denominator as a positive half power. Now this one is kind of like a decompose. It's got a single term denominator. So anytime you have a single term denominator, you can rewrite that as x squared plus 4x minus 3x to the negative 1. So I took that single term denominator and divided each term independently to reduce that down, then find the derivative of 16x plus 4 plus 3 over x to the second power. So all of that's pretty simple. We're going to switch gears here and talk a little bit about sine and cosine. I'm going to have you prove how the derivative of sine is cosine, and the derivative of cosine is negative sine, and the derivative of tangent is secant squared x. We'll take a look at how we know each one of these in just a minute. But first I want to take a look at the graph. You notice how the graph is increasing here? Increases. And then here the slope is 0. And then the function's decreasing. And here the slope's 0. And then again here the function's increasing. So this is a picture of my sine of x. And I'm paying attention like we did last class where we're graphing derivative graphs from the function graph. So if this is my function graph, y equals sine of x, I'm saying this is my derivative graph, cosine of x. And here's how I know that. The graph is increasing, so the slopes are positive, which means if this is my slope graph, I have to be above the x-axis until I get to the 0 slope, and the 0 slope is pi over 2. You see how that's an intercept? And we said last class that a maximum or a minimum would be x-intercepts on our derivative function. So I know that I've got an x-intercept at pi over 2, and I have an x-intercept at 3 pi over 2. My function graph is increasing, so the derivative graph has to be above the x-axis. And then my function graph is decreasing, which puts our derivative graph below the x-axis. You see where the function changed from concave down to concave up? At that place, which is pi, we had a minimum value on our derivative graph. And then again, where the function increases, starting there, I need to have, starting at 3 pi over 2, I need to have my derivative graph above the x-axis. So this is just a graphic interpretation of how we know the derivative for sine of x is cosine of x. And here again, I'm showing two different approaches for finding a derivative on a calculator. And I can do that graphically using the numeric function key on the 84. In my graph window, I'm asking the calculator to graph the derivative of sine, and on my TI Inspire, I'm doing the same thing. In the graph window, I'm asking the calculator to graph the derivative of sine. And you can see right here, it's going to give me the cosine curve. The derivative of sine is cosine graphically. And here's where we're going to prove it. So we know from pre-calc that you had the sine of two angles, and that formula went sine, cosine, cosine, sine. So I could write that rule, sine of x cosine of h plus cosine of x sine of h. Sine, cosine, cosine, sine. And then the cosine function went cosine, cosine, sine, sine. Cosine of x, cosine h. And what happened on this? When this was plus, we had to switch to minus. So cosine, cosine, sine, sine. Sine, cosine, cosine, sine. Cosine, cosine, sine, sine. Cosine, cosine. I know my students think I'm crazy. So we want to use those rules and remember also that, let's see if we have that on here. We need to also remember these two rules. That the limit as h approaches 0 of the sine of h over h is 1, and the limit as h approaches 0 of cosine h minus 1 over h is 0. So these were two rules that we found in our textbook. So let's first do the sine function and show that the derivative of sine is cosine. So we want to find f prime of sine using the limit process as h goes to 0 and sine of x plus h minus sine of x divided by h. So that's where these two rules come in handy. Sine, cosine, cosine, sine. Remember, we're going to keep the limit notation until we get ready to use the limit. So sine of x cosine of h plus cosine of x sine of h minus sine of x divided by h. Hey, how about that great straight line? Sometimes I can draw a straight line, sometimes I can't. So do you notice how this term has sine and then subtract, and this term has sine? Let's pull that sine out into the front. So the sine of x times cosine h minus 1 plus the cosine of x and the sine of h. And this is divided by h. So a trick that's great in calculus is we can take this sum and break this up into two different fractions and take the limit of the two different fractions. So that's going to be a very beautiful thing. The limit as h approaches 0 of the sine of x times cosine h minus 1 divided by h plus the limit as h approaches 0 of the cosine of x sine of h divided by h. See how I got that? It's like a plus b over c is a over c plus b over c. I see this fraction and this fraction. We're taking the limit of each of those fractions independently of the other. So what happens? I said this was a beautiful thing. I can also do the same thing with the product. So if we take the limit as h approaches 0 of this little piece in here, you see that rule? The cosine of h minus 1 over h is 0. So what does that do for us? That means I'm taking the limit of the sine of x times 0, and all of that's gone away. So this entire term is now 0. So that's a beautiful thing. So this piece is 0. Plus, we have this limit. So there's that rule again. The sine of h over h, the limit as h goes to 0, we said is 1. So this piece is 1. And we have cosine times 1. So this is cosine of x, because there's no 0 to plug in for our x. So we just proved that the derivative of sine is cosine. Now, are you really brave? If so, turn off the video and give this one a try to show that the derivative of cosine is negative sine. Then come back to check with me after you're finished. Good luck. Okay, again, I'm going to employ that rule of the cosine of x plus h minus the cosine of x divided by h, keeping the limit notation until we get ready to apply the limit. This rule is cosine, cosine, minus sine, sine, minus cosine. We're going to try to group common terms together. So in this case, we have cosine between the subtraction. That's going to give the limit as h approaches 0 for cosine of x times cosine of h minus 1 divided by h. And then I'm going to split it up right now as minus, well, maybe we should write the step, minus sine x sine h, and then break it up into two separate limits. So we have cosine x cosine h minus 1 divided by h, and we're subtracting the limit as h approaches 0 of sine x times sine h divided by h. And using the properties, when h goes to 0, this limit goes to 0. When h goes to 0, this limit goes to 1. We have 0 minus the sine of x. Therefore, the derivative of cosine is the opposite of the sine. It's a beautiful thing. Then our last example is just going to be the natural log rule. Anytime you have the derivative of y equals e to the x, it's the only function that has itself as its derivative. So if f of x is e to the x, then f prime of x is e to the x. Also, we want to know that if f of x is natural log of x, then the derivative is 1 over x for all the positive x's, since we can't take natural log of negative numbers. So these 6 examples would be f prime is natural log of x cubed. Remember the properties for natural log, that you can bring the exponent out as a factor, and then natural log of x. So if the derivative for natural log of x is 1 over x, then our derivative for 3 times 1 over x is 3 over x. So f prime of natural log x cubed is 3 divided by x. On letter B, we have a product there, so I want to think about g of x is the natural log of x squared, and when I have a product of a log, I can call that the sum of two logs, e to the x. Again, using properties of logarithms, this is 2 natural log of x plus x natural log of e. Now, what do we know about natural log of e? So g prime of x is 2 times 1 over x, but natural log of e is 1, so the derivative of 1x is just 1. You noticed I did all of the rewriting I could and then took the derivative. On letter C, hey, what's going on here? On letter C, natural log, derivative is 1 over x. We're going to rethink this as negative x to the negative 1. So that's going to give us a positive 1 x to the negative 2, or 1 over x squared. I would just leave it like that and not bother getting common denominators or anything. Letter D, same thing. I want to rewrite the log of a quotient is the difference of the logs. So natural log 2 e to the x minus natural log 3x. Again, the log of a product is the sum of the logs. Natural log of 2 plus natural log of e to the x. Same here. The log of a product is the sum of the logs, but we have subtraction. So minus natural log 3 minus natural log x. Then when you think about properties, this is just a number, natural log of 2. So the derivative of a number is 0. If this x comes in the front and natural log of e is 1, then the derivative of x is just 1. The derivative of a number is 0. And the derivative of natural log of x is 1 over x. So how simple is that? I've got y prime 1 minus 1 over x. Because all of these other things, constant, constant, those went to 0. Okay, 2 more, and then we'll be done. In this case, we've got the natural log of a product. So breaking that apart, let's call that the natural log of 4x cubed plus the natural log of e to the x. Breaking this term apart, natural log of 4 plus natural log x cubed plus x natural log e. This is 1. This 3 comes out here. And then we have natural log 4, 3, natural log x plus x. Now we're going to take the derivative. F prime of x is 0 here. This is 3 divided by x. This derivative is 1. Pretty simple. And then letter F, our last one, we have g of x is pi e to the x, and rewriting this, it's going to be x to the negative 2/3. So just to get a look at it, then we'll take the derivative. G prime of x is pi e to the x, because the derivative of e to the x is itself. This is going to give us positive 2/3. And take 1 off of that is 3/3, so we'll have a 5/3 in the denominator. So good luck with practicing. I'll see you next time for product and quotient rule.